Next speaker here is André Buhart, F1ATB, and the work of André is notable for a very interesting reason. It's also a piece of software for web, sorry, not for web SDRs. Yes, for web SDRs. Yeah, of course, for web SDRs. Because it's not like, it's a little like OpenWebRx, but it's not just a receiver piece of code, it's also a transmitter piece of code. So this is actually the cornerstone of every project you want to make that brings transceiving with an SDR to your idea. So for example, what I did last year, I built a base station for the QR100 that is remote operable, and I was using André's software, and I found it so cool that I said, hey André, you need to speak to our audience. This is really a cool thing. So please welcome André Buhart here on the stage with us. Hello.
Yes, hello. Hello everyone. So my call sign is F1ATB Bravo, and I'm pleased today to present to you RemoteSDR. RemoteSDR is a software-defined radio receiving but also transmitting. Just behind me, you have, for example, QO100, my QO100 station transceiver in live. It's exactly the situation in live on Q100 just now. And I can even transmit, if we have time at the end, I can do a transmission. So it's a system which is driven, controlled just by a web page. Use Chrome web browser and that's it. And you can use it, you can control it from your smartphone if you want. And you can cover any band covered by your SDR. So maybe I suppose now it's time for the video, which will present more in detail this solution, and after I'm open to the question and answer. See you later.
Okay, very good. So also in this case, we have pre-recorded André's talk, as always, as usually. André will be here after the talk to answer your questions. And now, dear video team, play the pre-recorded talk.
Hello everyone. My call sign is Foxtrot 1 Alpha Tango Bravo. Today I present RemoteSDR, SDR software-defined radio controlled remotely using a simple web browser. Classical situation, we have an antenna and we have to connect this antenna to the transceiver in your office at home. And sometimes the distance is quite important, particularly when you work in VHF, UHF, or higher. So this is a difficulty, and we have one solution to solve this difficulty is to implement an analog to digital converter close to the array in order not to transfer HF signals, but digital signal. If we take a simple example like the 2 meters band with a bandwidth of 2 megahertz, and we apply the Shannon rule to sample the data on the array. We have 2 megahertz band multiplied by 2.4, which is the coefficient we need to respect the Shannon rule, 16 bits. We arrive to a data rate of 76 megabits per second. This is quite important. It's feasible, an important data transfer from the antenna down to your office. One solution to solve that difficulty is to add signal processing just behind the analog to digital conversion in order to reduce the data, the amount of data transfer to exactly what we need. And for a transceiver or receiver, we need simply an audio channel. An audio channel of 4 kilohertz is sufficient for the bandwidth, multiplied by 2.4, the famous Shannon coefficient, and 16 bits. And so we arrive to data rate of 154 kilobits, which is needed. On the spectrum side, if you want the complete spectrum of the 2 MHz band, on, for example, 2048 samples, we need, and we use only, or we implement only 5 samples per second, which is quite sufficient for the display. And we arrive to 163 kilobits per second. So in total, we have a little bit more than 300 kilobits per second. That's our need, and not 76 megabits. So it's interesting to implement a signal processing close to the analog to digital conversion, close to the antenna, in order to reduce the data flow to your office or to your shop. Here on the PC, you can implement the graphic processing. We need it to display all the information, and we can add also some signal processing. We will see that later. The signal processing at the beginning. At the beginning, we have to filter the band, 2 megahertz, around 145, and we multiply this signal by 2 signals at 145 megahertz. One I call sine and other one cosine. It's exactly the same, except there is a phase shift of 90 degrees. It's like a complex demodulation. And here we generate 2 signals, 2 branch of signals, a low pass filter of 1 megahertz, an analog to digital converter, here also the same. And so we obtain what we say a complex data, which represent perfectly the bandwidth of 2 megahertz, but completely translate around 0 megahertz, around plus and minus values around 0, and even negative frequency. But this is due to the complex representation of the data we have here on the right. So this is the first step of the processing we have to do, and this is perfectly done by the SDR. The SDR on the receiver side, this is a job which he's doing. On the SDR, we have a lot of SDR on the market. We'll put here the one I can control with RemoteSDR, SDR dedicated for the ham radio domain. The famous one, RTL SDR, the cheapest one. We have also the F1, an interesting solution which can go up to 6 gigahertz in receiver mode, so it's interesting. The only constraint with these two is that the dynamic is limited to 8 bits. So the total signal, the difference between the minimum signal and the maximum signal at the same time, is limited due to this 8 bits only. If you want higher dynamic, we have Adam Pluto, for example, which can work in Ericsson TX, well known in the ham domain, and the RSP1A. Both have better dynamic to cover in a better way, let's say, the small signal and high signals arriving at the same time on the antenna. So behind the SDR, which provides the complex data, we just saw that, we will separate in 2 branches the signal processing. One branch is dedicated for the audio channels. We multiply the signal by the frequency of the audio we intend to receive. We have a low pass filter to limit the audio band at 4 kilohertz, and you obtain an audio channel of 10 kilo sample per second. It's a very simplified representation of this receiving channel. I have no time to completely describe it. The second branch is for the spectrum. The spectrum, as I already mentioned, 5 spectrum per second is sufficient. So we do FFT, fast Fourier transform. So the fast Fourier transform convert 2048 samples in the time domain in 2048 samples in the frequency domain. So it converts the time domain to the frequency domain. This value of 2048 corresponds to the power of 2, and simply because the fast Fourier or the Fourier transform is simplified. That's why we call it fast Fourier transform when the number of samples is a power of 2. It's a problem of mathematical computation. So we have the two outputs here, audio and spectra, as we need, at a rate which is acceptable and not so important, so which can be easily transferred outside. All this signal processing, I have not for all the signal processing, I have not developed all the code. I used GNU Radio. It's a fantastic tool to develop radio processing. You have elementary boxes which represent a function like filtering, complex data to float data, multiplying function, a multiply function, add function. So you just have to draw a link to connect this box together using your mouse, and you create your signal processing. It's a fantastic tool. I recommend you to investigate sometimes to analyze it. And behind here we have the signal processing for the receiver. We have the FFT domain, the FFT processing, and so on for the spectrum. Take signal processing. We use the same structure, also GNU Radio, but it's far more simple. We have modulator either in SSB or in BFM. We transfer the data to the SDR. We inject we drive the SDR by the frequency here, and so this SDR will generate this HF signal on the transmitter. We can use an add-on Pluto or an AKF1. I have put also S818, sorry. It is not an SDR, it's a simple NBFM receiver and transceiver, which is very cheap, I think less than 10 euros. It can connect it to RemoteSDR as a transmitter. So if you want a system which works only in NBFM, it's a very cheap and interesting solution. All the signal processing, as already mentioned, is done by GNU Radio. To manage all this system, we need some software, and we need a server, data server, in order to transfer outside all the data we have processed. So I use now Node.js, which is also an open source code, which is quite interesting, flexible. Previously, in previous version RemoteSDR, I used Apache, PHP, Python, and so, but I have suppressed everything and replaced by Node.js, which is in our case more efficient. All this, the code generated by GNU Radio and I developed on Node.js is implemented on Orange Pi 02 RMBian processor, or you can implement on the famous Raspberry Pi 4 with a memory of 2 GB with Debian Bullseye as the operating system. Very interesting hardware. But currently, since the COVID-19 pandemic, we have some difficulty to purchase this model. Everybody expects a better situation by the end of this year to be able to buy such a processor at a reasonable price. So this processor will be able, by the server implemented, to transfer all data to your PC. There is no need at all to develop a specific software to represent graphically the information. There is a fantastic tool we have now on your smartphone and your PC, which is a web browser. A web browser is extremely powerful. There are different web browsers. Not all of them are perfectly respecting the W3C standard. Me, I prefer to use Edge on Chrome. With Firefox, I have some difficulty and I cannot develop different software according to the browser. So I developed RemoteSDR to run on Edge or Chrome, which are very similar browsers. You know that browsers can process HTML data, CSS for the graphic CSS language. That's a classical function to generate a web page. But a web browser can do far more. First, you can do computation using JavaScript language. And there is one point nobody knows, but in JavaScript, we can also implement very interesting function signal processing function like FFT, filtering, oscillators. In one line of code, you have an FFT or an oscillator. So it's very simple. Nobody knows that, but it shows how the web browser are powerful today. And as already mentioned, it works on your smartphone, on your PC, on your Mac. So JavaScript to display the data on your system. Here are the example of the result. We have the main receiver here, the parameter of the receiver, the parameter of the transmitter, and here some surveillance of the processing. I'll show you now in detail. The spectrum, we have the A scan, so amplitude versus frequency here, and the famous waterfall to have the history of the frequency domain versus time. We can zoom or unzoom the spectra from band total from 200 kilohertz up to 2.5 megahertz. Here, for example, is on Q100. We have a band of 500 kilohertz display. In every case, we have 2048 frequency beats to cover, which correspond roughly to the accuracy of your display. You can have a function, for example, you have a scanner, which even work in city-side bands, and not so bad. Even in SSB, even the frequency is not exactly steered, you can understand. So a scanning function for NBFM and a city-side band. You adjust the frequency. Here, the frequency of the audio channels. You can adjust the central frequency of the spectrum, the bandwidth of the spectrum. Here, the different modes of receiving: CW, LSB, USB, amplitude modulation, narrowband FM, wideband FM. Here, you can adjust the audio gain when you are receiving and when you are transmitting, because this system can work in full duplex, receiver and transmitter at the same time. Here you have also additional function, an equalizer, and you can modify the spectra of the receiving audio in order to adapt to your correspondent. You can also filter it with some notch filter, noise filter, the audio channel. And you can also send the audio channel without any filtering to an external processing, for example, for FT8 or SSTV decoding on another software. The control of the receiver, more in detail. There is one point here which is important, which shows how the data are received. If the flow of data you receive from the Raspberry Pi is continuous, or if there is some interruption. There is a buffer in the system to absorb the various flow of data, but this buffer is limited in size because we cannot, or your correspondent cannot wait until the end of the buffer when he wants you to transmit. So you have to reduce the size of this buffer. But the size will be adapted to the quality of the flow of data received. Here the quality is good. Here using, for example, Wi-Fi, the quality is not so good. So it's why I recommend to use a network, an Ethernet network, which is wired instead of the Wi-Fi. It works with Wi-Fi, but you could have some impact on the data flow of data. It depends how busy is your Wi-Fi at home. You have also some spectral analysis of your correspondent, time representation of the signal, here frequency memory to enter your favorite frequencies. If you're working in very, very high frequency, for example, in Q100, you have some problem of drift of frequency versus time. And so, for example, Q100, you can track your receiver or control or correct the drift of frequency of your receiver by tracking the beacon, the frequency beacon transmitted by Q100. For the transmitter side, Here you have the frequency of the transmitter, you have the time representation of the signal of your microphone, the frequency representation of the signal of your microphone. You have different tone generator, DTMF to open a relay, the old 1700 Hertz generator. We have a single tone or double tone test in order, for example, to test the linearity of your SSB transceiver. And we can transmit in CW, SSB, NBFM, and RTTY. We can also adjust by an equalizer the quality of the audio coming out from your microphone if you want, and you can also inject audio coming from the outside from another software, for example FT8 or SSTV. Here an additional feature, simple box I've developed because some are preferring using rotary knob to adjust the frequency instead of the mouse. Every ham radio guys have the habit of turning a rotary knob, so using a simple Arduino and a rotary knob like this one, you can modify the frequency of the remote SDR. You are connected using a USB. In addition, I have put a connector to connect a key for a CW key in automatic mode also. Here on these two pages, I will not develop in details, but these two pages allow you to test the SDR, to test the transmitter. So you have different testing functions to verify that the system is working correctly. And you have also an important page for the settings, because according to the type of SDR you connect on your system, you can work from 100 kilohertz up to 6 gigahertz. So you have to define in which band you want to receive and transmit. So this is done here, and you can put also some marker, frequency marker on interesting frequencies and so. So you have a lot of parameters you can inject in your system to personalize remote SDR to your proper usage. Here an example of remote SDR for QSL. I have other at home, for example, the 2 meters band or the 70 centimeter band. This one for Q100 was my first one. Here the receiver side, so the satellite dish, the receiver uses HRF. 8 bits is sufficient on Q100 because there is not an important dynamic between low signal and high signal. As the signal are processed using a Raspberry Pi now, and for the transmitter is the same. I have an HRF1 Chinese version, which are far cheaper than the European version. And here different amplifier in order to reach a level we need for the transmitter, and the filter also bandpass filter. And here by the internal network in my house and can connect any laptop or desktop PC or even my smartphone via Wi-Fi in order to listen and transmit on Q100. So if you need more details and complete documentation, the software to implement, which is open source, and to implement on your Raspberry Pi or Orange Pi, you go on F1ATB.fr. This is my website. You will find all the details and documentation. We have also some video on YouTube on my channel. So thank you very much. Listen to me. I hope that will invite you to see how remote SDR works in detail. You can go on my website here and listen to Q100, the system I have at home. You cannot transmit, you can understand that, but at least you can listen. Thanks again to listen to me.
Okay, André, so thank you very much for this very interesting presentation. Yeah, as I said before, I know your system because I built it up myself. And in fact, you answered one of the questions I wanted to raise. That was about how to control CW with it. And we need to talk about this later, and how to build the little Arduino and the pedals and all those things. I would be very interested to do that myself. Okay, so this is actually really a very interesting project for that solves the problem which many of us have that live in bigger cities. Because when you don't have the space to build up an antenna or a system where the transceiver, whether or not be it an SDR transceiver whatsoever, but where the transceiver cannot be at your home because you don't have the possibility to set up the antenna, then this is the thing that solves your problem. Because then you can just put it up somewhere else outside in the countryside, somewhere, anywhere, and use a web browser and control it from home, or actually wherever you are. And what I did, I integrated it into my VPN. So basically, it doesn't matter where I am, I can always use it as long as it's running. In the moment, it's not plugged in, but okay, it's a different story. So one thing I would like to add, a little feature request maybe, is the user management. So in the beginning, when you log in, you have to identify yourself, which is good. But I would like to have some kind of hard access control. And this actually is something that limits the use a little, because you can't just place it somewhere out in the internet and open a port through your DSL router and make it accessible, because then everybody can use it. Maybe this is something you could implement in the next version. But that's just my comments, but we're not here to discuss my things, but we're here to discuss the questions of the audience. So, are there any questions?
Thank you. Good afternoon. This morning I presented the Saturn radio here, which is essentially a baseband SDR using an FPGA for receive and transmit, and a Raspberry Pi local processor. It seems to me, if I was to take your software and modify the interface to the SDR, I would then be able to operate that remotely. Have I understood this right?
Yes. The only difficulty is to develop the piece of code to make the interface. After it's adapted currently RemoteSDR to manage different type of SDR, so we just have to put a part of code just to adapt. And this is part of my job also, is to see what is the SDR market today, and to slowly add different or new SDR to open my system to different solution. The difficulty today is to find good SDR on the TX side. There is a lot of on the RX as a receiver. On the TX the market is more limited if you want to speak with a reasonable price. That's it. And just to come on the previous remark today, I mentioned that the system is not protected, highly protected on the receiver side. Anybody can receive, more or less, but to transmit, you need to enter a password in order to be able to transmit. So I am the only one to know which is my password for my transmitter.
Any more questions?
Thank you for your software. On your webpage, you always have examples where the Adam Pluto is connected via USB to the Raspberry Pi. Is it also possible to connect it via Ethernet?
No. Today, the system works only with a USB connection on the Pluto. And I have to say, it's often a difficulty because data rate is quite important, and according to the power supply you have for your Pluto and the type of cable, the quality of cable you have between the Pluto and Raspberry Pi, sometimes there are some difficulties, but which can be solved. Any other question?
No more questions? Okay, so then thank you very much, André. And great piece of code. Thanks for programming it and helping me with my QR100 project. Really cool thing. So
and behind me, it's a QR100 live. Huh?
So, okay, good. Then thanks very much.